So in that vein, STM, so CubeAI is another framework that's very widely used and popular as well. Now, Danilo, who is from STMicroelectronics, is going to talk about the framework and sort of how optimizations are done there. So Danilo, thank you for making the time to come over here. So Danilo is really well known in the community. He's done many things. So if you look at deep learning is one of the hot things now. But if you kind of date things back, there have been other major thrusts like this where some sort of application domain becomes extremely critical. And the one that he kind of talks about in his bio sketch is actually about the MPEG standard. So, anything around video encoding, decoding, or audio encoding, decoding, like these are extremely big standards, right? Like because they're actually used heavily. So Danilo, I didn't know you actually were involved in developing the MPEG standard. That's pretty cool. So Danilo has been driving a lot of the work at STMicroelectronics around both the software stack and kind of looking at some of the aspects on the hardware side. So he's very deep inside the TinyML space. He's actually been working both with academics, students, and actually enabling this ecosystem. And it gives a very different perspective. For instance, as compared to what we'll look at next class, where Pete's going to talk a lot about the TensorFlow-like micro, which takes a very different approach. But today, we'll focus more on what CubeAI framework does. Danilo and Pete, do you want to add anything? Because you also worked with Danilo quite a bit.
No, I mean, Danilo has been an awesome contributor to this whole sort of TinyML movement. ST have been like really leaders in this space. And so, yeah, I'm really excited. I think I'm hoping and I'm expecting I'll learn a lot from this talk. So I'm really excited to hear what Danilo has to say.
Awesome. Thank you, Danilo. I'm going to stop sharing and then hand it over to you.
Yeah, thank you so much. I need to share my screen, I think. Yeah. Okay. It says that I am disabled on screen sharing.
Can you try again? I think I just may have.
Okay. Yes.
As usual.
Screen 2, yes. Screen 1. Okay, this one. Share. Okay, it seems I'm sharing the right screen.
Yeah.
Just don't hesitate to let me know if there are troubles in sharing the screen. And let me go in. Oops. In. Just a second. Okay. No. This one. Do you see the screen?
No, we see you.
No.
It was working a split second ago.
Yeah. Just a second.
Well, Danilo brings it up. For the folks, I know like being on cam and stuff kind of gets tiring after a while. I've certainly seen like students are kind of off camera. But please try and be on camera. It just kind of helps us engage with you a bit better. Just a request.
I prefer to stay in this mode. Otherwise, I think I got confused sharing my screen. First of all, thanks a lot, Vijay, Colby, Pete. Is really a huge opportunity to have the availability of this slot and to share basically what I'm doing and my experiences on tiny neural networks and tools. I'm based in Milan, and I take care about the technology that ultimately is integrated on two tools that we distribute, serving a couple of family in terms of microcontrollers for IoT and automotive. So the first thing I would like to share with you is this a technology, I mean the tiny machine learning and the tiny neural network, a kind of trendy technology or a singularity? The difference between the two is that a singularity poses a completely new perspective on a certain technology, and maybe poses also the need to acquire skill and competencies that will be useful for years. So let me bring on the table some elements that try to stimulate your thought in terms of judging in which one of the cases are we. And to understand a little bit more where we are, I think we need also to consider the history of machine learning, starting from Alan Turing defining the Turing machine and the Turing test, which philosophically defined the problem of approximating a certain behavior. Then in 1957, Rosenblatt defined the perceptron. If you see the intimate nature of most of the neurons that we use in artificial neural networks, this have been deeply inspired by Rosenblatt work. Then at the end of the 80s, George Cybenko defined the universal approximation theorem. And this cleared, at least in my mind, a lot, what are the neural networks. Then, you know, the founder of Google pointed that everybody knew, including himself, that neural networks were existing. However, they were not working. And the application were almost zero, if not zero. And there were reasons about that. We didn't have the wonderful tools that we have today, such as TensorFlow. We didn't have wonderful hardware accelerators, such as GPUs, TPUs, and so far. At the time, the graphics unit were just image blitters. And another important point, we didn't know how to initialize correctly the neural network. So it was a paradox, because to let them converge, basically we need to know the starting point, which was closer to the optimal point, which is a paradox itself. Then with Geoffrey Hinton in 2006, neural networks started to pop up because thanks to his study on autoencoder restricted Boltzmann machine, the technology started to fly through many contexts. And I would point out that one of the most exciting technologies from an industrial point of view was the Google AI assistant, which really was one demonstration, practical demonstration in industry, that the Turing test was solved. And I'm not saying that because, Pete, you are here, but this is really the argument I use when I do such kind of lessons, because I think these points are the breakthroughs that let us to understand where we are in terms of artificial intelligence. What's next? Well, you know, sooner than later, as I would imagine, the robots, for example, the one from Boston Dynamics and so on, are really the next frontier, which is closer than what we thought in the past. However, I'm not here just to show a practical example through our tools, but also to remind a little bit of theory, because doing only theory is useless. A little bit of practice without theories is dangerous, because you don't know what really you are doing. So very short, take a transfer function which modelize analytically whatever results you want to achieve. We know from mathematics that through a Taylor series, we can approximate such a function with an error small at your will. However, what happens if this transfer function is not analytically modelable? For example, this is the picture of my cat. The label, the name of my cat is Luna. I'm unable to analytically modelize the transfer function. So no transfer function. How to approximate it? Thanks to George Cybenko, 1989, we know that exists at least a single layer perceptron that approximate with an error small at your will the transfer function, which is hidden in the sense that is hidden in the data we have available. Now you can understand how the data now pop up in their full importance. After George Saibenko, Hornick expanded the existence of a single layer perceptron in multi-layer perceptron, generalizing also the nonlinearities. As I said, we are back on 1990, but it took years before these things really impacted our life. So there is a strong history behind that everybody of us should remind. After this small excursus, let's enter in more practical things. So first of all, I don't speak too much about Internet of Things. I prefer to use the term of cyber physical systems, which are composed by three domains. The physical domain, for example, the room in which we live, the town in which we move, and so on, which are sensed by units. These units, which may be consumer goods, are made of three components: sensors, computing device, communication mean, so that the raw data from the sensor are conveyed through the computing engine through a network. Then these are sent to the cyber domain, where usually intelligence is implemented because resources are unconstrained. There is the memory, the computing power that we need. If you are familiar with Colab, you can have access to powerful machine set in a very easy way, and that's what you can do, and you can do a lot with such an environment. You can and I do daily put my intelligent algorithm there, preparing some results which are conveyed back to the object domain. Obviously, I'm interested on the intelligence on the object domain because as ST, we produce a microcontroller and sensors. But today, the situation is as such. Is it proper to centralize the intelligence? No, that's totally wrong. And there are reasons. One practical example, imagine that you have a machine that has a rotating shaft and you want to control, monitor the status of the bearings. So, for example, we place a couple of accelerometers and we sense the rotating shaft through the accelerometer, producing an awful amount of gigabytes per day, close to 30 gigabytes per day. That's for continuous monitoring. Imagine that we wanted to, for e-mobility, battery management is rising in its importance. That's a typical battery system that is used in student formula in a formula kind of one for races. The car is totally electric and battery powered, and we have in the BMS 24 slaves, each one with 6 cells, and typically the data rate is very low versus the previous example. However, the processing is really time critical. In less than 200 milliseconds, the energy from the battery has to be distributed intelligently to the different wheels. So the latency is another quite important point. And as I said before, the sensing unit are not just a single sensor attached to a microcontroller, attached to a communication means, but we have a plethora of sensors, each one a different data rate that can be few samples per second up to 30 kilohertz, 30,000 samples per second, or even in the audio domain, even more than 40 kilosample per second. So there is a strong variety, a variability of data rate. And we needed to handle, and this created ultimately a thunderstorm on the cloud. So I think there is very few debates on the need that we need to delocalize the intelligence. We need to distribute the intelligence down where? Close to the sensors, inside the sensing unit. When we speak about tiny machine learning, after all, we are interested in deploying the neural networks in the sensing unit. And the first computational unit inside the sensing unit to be considered is a microcontroller, which doesn't mean to copy the neural network which run on the server down into the sensing unit. That's impossible because they are too complex. If we carefully rethink them and re-engineering them properly, there is a lot that we can do in putting the intelligence, the neural network in the sensing unit. And this is an example I would like to run with you. First of all, when this is possible, it's possible to map neural networks on microcontroller if three conditions are met. The first two seems obvious. There should be enough memory, read-only memory and random access memory to store respectively weights and activations, which are needed by a pre-trained neural network to run the inference. The third is a little bit complex, but it says that the inference time should be less than the time of arrival of the samples from the sensor to the microcontroller, which means that the more power in terms of floating point operations per second I have in my microcontroller, the better it is. Okay. On the other side, I should try to lower the complexity of the neural network. And this is challenging by an ever-increasing need of sensors which are producing more and more samples per second. If this equality is not respected, then we need to find way to increase the MCU computational power. How? For example, adding hardware accelerators attached to the microcontroller. Otherwise, this can be done can be achieved in pure software. Now, let's consider the subset of supervised deep learning, which means that we train offline the neural network and then we try to deploy on meaningful use cases. The methodology can be, to achieve that, can be subdivided in 5 steps. Define the application, which ultimately means I'm selecting some sensors. Then with those sensors, I get enough data with a strict policy in terms of collecting them and labeling them. Because exactly in this way, I got input and a correspondent output, which underlie an hidden transfer function that I hope my neural network that I'm trying to design will approximate. The third step is then I use an environment, a deep learning framework to design my neural network and to train it. Now, from an industry point of view, there is a clear evidence, also in my experience, that TensorFlow has got the maximum impact. There are also other tools coming. However, I would say that it has still to be demonstrated the impact on the industry, and I'm referring to PyTorch. There is also another tool, which is MATLAB, that is more and more impacting the developer, especially in the automotive industry. So I'm going to focalize my attention on TensorFlow. After I got a pre-trained neural network, how can I program my microcontroller? There are few things to be done. You know, there are different approaches. One approach that we implemented is through code generation. So we took a neural network, which is embedded in a certain file format, and then we generate C code. C code that can be ultimately compiled with an IDE on the target microcontroller. So respectively, step 4 and step 5. This technology of code generator, we embedded and distributed free of charge in 2 tools. One is the STM32Cube.ai for the STM32 microcontroller family, which is based on Cortex-M ARM microcontroller, and the other is SPC5 Studio, which target automotive grade is MCU based on a total different instruction set from which is a derivative of PowerPC for automotive application. So you see that to target 2 different microcontroller, we actually, it was obvious for us to create a methodology, a tool chain to convert this file format, for example, the Keras file format or the TF-Lite file format or the UNIX file format into C code and libraries that can flexibly be retargeted on the microcontroller of choice and on the IDE of choice. So let's go through an example, and this example is a classification of images. These images captures saline bottles that encloses a saline solution that are used for intravenous drip. The dataset is public. There is a publication in Data in Brief that describes the dataset. So you are free to also get it free of charge if you are interested. This is to support the practical example. So the dataset is composed by 4 classes depending on the level of filling of the bottles. 50%, 80%, 100%, and were captured at high resolution and balanced in order to have, in order not to bias the learning process toward any of those specific classes. So these are equally represented. The methodology that we used was based on modelizing the network in Colab. And in Colab, we used the TensorFlow 2.3.0, and everything is possible. Maybe this picture is quite complex, but it says that I can train my network in TensorFlow, export in TensorFlow Lite, using even at full precision or at int8 precision with post-training quantization on or training-aware quantization. Or I could use an high-level API, which are based on, which are the Keras API. Keras is part of TensorFlow, and export the model in full precision. But then I could also re-import in TensorFlow, convert in TensorFlow Lite with post-training quantization. So this provides a lot of opportunity to train and deploy the model at different bit depth depending of my need. Obviously, if I'm quantizing a network, what I gain immediately is the footprint. 4 times the footprint, because I'm moving from containers full precision FP32 to int8. So 4 times the footprint, but also the runtime memory I'm gaining 4 times, and the execution also I'm gaining because I'm going to exploit the DSP function which are made available in the Cortex-M. Sometimes developer use also the post-training quantization procedure that we embedded in Xcube AI, but the let's say the integer format is fully aligned of the one in TensorFlow Lite. So let me show one example. In this on the
we go into the next slide. Can we go back to the previous slide, please?
Yeah.
So this question goes out to Pete and Danilo, both of you, because often I think a lot of people don't quite realize the complexity that sits at the interface in terms of syncing one file format into another. And I was wondering if you two could comment from a production standpoint what it looks like. how easy is it really to be able to take the files and move them from one framework to another?
I can comment in my experience. Every time I do a development, first of all, I am an hardware guy, so you can imagine that I'm not totally comfortable with software development. However, the example I played with allows me to conclude that moving from the full TensorFlow and the Keras environment is very easy to learn and is well documented, especially with the TensorFlow 2.3.0. Before was a little bit tricky, but the things were improved a lot. And in particular, and in fact, that was the reason before we introduced the post-training quantization in Xcube AI. But as soon as the deep learning framework was further developed and documented, the examples are very simple. My students are able to play with those pipeline in very few weeks, I would say. And for me, this is an important sign because, you know, in the community we serve, in the embedded developer community we serve, really things has to be easy. These guys are not, with total respect for the PhD, are not, do not hold very high level education or a PhD or post-PhD experience. So doing the things easy is important. And if one student of mine can do that in few weeks from scratch without pre-knowledge, it suggests that the productivity is at the right level. And that's, I think, is why people are more and more familiar with these people in the embedded system space are more familiar with TensorFlow, because at the end, the things are getting easy for what one needed to achieve.
Pete, you're muted.
Thank you. Yeah, exactly. And I think I would add to that. It's actually a lot harder for researchers who are coming up with like new models. If we are able to identify kind of existing models and provide a well-lit path, then we know that the operations and things that people are using are going to be convertible. The big problem comes in that TensorFlow has over 2,000 different operations that you can actually use within the training environment. And TensorFlow Lite only has about 130 operations it supports, and TensorFlow Lite Micro only has like 55. I don't know the exact number that Cube AI supports, but you know, there's almost nothing that I'm aware of supports all 2,000. You know, so what really is the challenge is if you've got somebody who's coming up with a novel model that's using one of these like kind of, you know, long tail of 2,000 different ops, and they tend to hit a, you know, an immovable barrier when they try and sort of export down to an inference framework. And I'll be talking a bit in my lecture about all of the pain that's involved in trying to figure out, oh, okay, I have to support one of these 2,000 different ops. Okay, what does it actually do? How do I export it and everything like that? So I don't know if that's sort of been your experience too, Danilo, or, you know, kind of how you think about, you know, people coming with their own models and saying, hey, this doesn't work.
I can comment in two ways. You know, the developers that are used to work with microcontrollers are not AI experts. So pretending to have a fast learner or too many operators is like killing them at the beginning, and this discourage them to do more investor. So we need really to do whatever effort we can to easier their life in terms of tools, but also in terms of examples. So, and I would like to tell in this respect an experience. When I hire students in my lab, the typical exercise is please design a network overnight and bring me some results. Obviously, in one night, also when I was a student, I couldn't become expert on AI. But this is a stimulus to see, look what is available around. What are the facilities, the tools that you can use? So if you combine Colab, which is free of charge, examples available in TensorFlow and in Keras, it's very easy overnight to set up an example and train a network, which suggests that the learning curve for simple application can be very fast. Obviously, then a guy need more time. But if the barrier to enter in this space is very low, then this will not discourage the embedded developer to move from their comfort zone, which is developing C, to develop AI application, because I think we are interested to have them in this space as well. So in my experience, if a student can overnight design a simple network, it means that also an embedded developer that, do that for work has got in front of him a very low barrier to enter. And this will definitely accelerate the adoption.
Great, thank you, Danilo. And yeah, so on that note, so for the next class, you'll be reading, you hopefully have started reading the TensorFlow-like micro paper. I think that paper, I would say the way you should look at it is like, it's got two key parts. So the first part kind of like really talks about these fundamental challenges and actually being able to deploy things. So a lot of what Danilo and Pete are talking about is sort of in that portion of the paper kind of does a really nice summarization about the issues that you see. And that's really kind of, I would say, almost independent of the specifics of what, Pete's team has done kind of like for TensorFlow-like micro. So try and keep that two separate things in mind as you read that paper. And Pete's going to go into a lot more depth in sort of Q&A around some of these challenges. Sorry, Danilo, I just wanted to make sure this
thank you
once, because they often blow through this, but it's actually quite critical that they get this.
I understand, and also the time available is short, so it would require much more time. Thanks for in-depth explanation, Vijay. So what I wanted to show now is an example. I don't pretend you understand all the bits in this example, but I would like to get you to get the feeling. On the left is a ConvNet, which is made by a pipeline of convolutional 2D layers with some 3x3 kernel size with a number of filters. If you modelize that with TensorFlow Keras and print the model summary on the data set I introduced before, the baseline model I designed was 1.2 million of parameters, 92% accuracy. Now, 1.2 million parameters means close to, in floating point 32, close to 5 megabytes of RAM. Now, the highest, the most powerful microcontroller that we got in the portfolio has only 2 megabytes of flash embedded. Obviously, I could add external flash, but let's keep everything embedded to keep very low the cost and the power consumption, etc., etc. So this network will not fit. Now, if I play with interleaving, pooling, and convolutions, I dramatically reduce the parameter number, as well as playing with reducing the number of convolutions and also the number of kernels I'm working. Well, if I move from a complex model to a less complex model, I would expect a drop in accuracy. That was not the case. I got in this example 67,000 parameter, but 90% accuracy. Now, this was an experiment. I'm not speaking about the confidence because, you know, proper validation procedure has to be run. But what I'm saying is that please explore any opportunity to reduce the complexity of the network, because the accuracy can be kept, and there are multiple parameters to play with in order to make it happen. You know, the complexity of convolutional layer depends on the kernel size, the number of kernels, and the size of the tensor I'm going to process with such filters. Therefore, if I play with the pooling, obviously a convolution expand the signal, expand because I'm playing with many filters on the same tensors, generating a replica of many tensors. But then with the pooling, I squeeze the output of a convolution to a more to a smaller tensor. So if I play with these simple rules, I can really squeeze my network. And in fact, then I developed the TinyOne. The TinyOne was now having 11,000 parameter, 92% of accuracy. Was I happy? No. I developed another one, squeezing the number of kernels, retraining, playing with other parameters, and I got 7,000 parameters, 94% accurate. Was that enough? Not at all. By using separable convolution, I can strongly reduce the number of parameters, because the separability allows me to save significantly parameters as well as complexity. And now I went down to 5,000 parameter, 96%. So starting from the baseline, they were reduced the pipeline with 67,000 parameter, TinyOne 11, Tiny2 6,000, Tiny3 5,000, and the accuracy was not dropped. So when I was thinking about moving, was suggesting to move the intelligence from the cloud to the microcontroller, with a careful design of the network and with a careful training of it, the network can be redesigned and accuracy can be kept. Now, have I under control all the implementation aspect? Not at all, because at this point in time, I know that I can measure the accuracy and I can measure the number of parameters the network that feature the network. That's not enough. Because I need now to understand how to map the neural network on the microcontroller. Now, obviously this can be done, for example, by uncrafting code. In fact, when I interfaced back to 2-3 years ago, the embedded developers that uses our microcontroller, these guys told me, look, we developed by hand the C code, we do our validation on a certain part number, on a certain microcontroller, depending on the requirements, and this takes 6 to 12 months of development. And the question was, and what happens if the requirement changes during the road and you need a more powerful microcontroller, or you need to add other features, other software on it? No problem was the reply. I restart from scratch my work, which is totally unproductive. So if we have a method that automatically map neural networks to code that can run on the microcontroller, we have the solution of the problem. However, that's not enough because the problem is a little bit more complex. I try to explain this. There are 4 basic requirements we need to satisfy. The first is to be interoperable with the AI community. I mean, as ST, we have no chances to influence the AI developers, and I'm sure no chance to influence Google and the others. So we need to interoperate, which means we need to be able to read the file formats which are exported from those tools. So that's the first requirement. As we interoperate with the deep learning tool, the same is valid to interoperate with the development environments that are used to program, to compile the code on the microcontroller. And this is another word because the embedded developers, which are not knowledgeable on AI, uses different development environment. And that's true for IoT, that's true for automotive, and so on and so forth. In my experience, I saw at least 9 different integrated development environment. Each one has his own rights to exist and are used by the community. So we cannot vertically integrate with those compilers. How to interoperate? Generating C code. So the tools that we produce, STM32Cube.ai and Specify-Studio.ai, essentially are C code generator. And then we leave the community, the embedded developer community, to compile those code with whatever IDE they prefer on the target microcontroller. That's the second requirement. The third requirement is that the tool has to be agnostic by the application. Why? Because the application is the added value of the customer. If I would teach a customer to do an application, actually, I would be the customer of myself. So we need to learn the responsibility of the application is on the customer itself. So we need to be agnostic on the sensors, which are a key gradient in any application, and the real-time operating system. So that's another requirement the tool has to respect. And in fact, it doesn't depend on any specific interface, sensor depending, on any specific interface, RTOS dependent. Even you could build an application without an RTOS. The fourth requirement is that since the microcontroller, as I shown before, is surrounded by a number of sensors, actually is a sensor hub. So anyone could design a specific neural network depending on the sensor. If I have in my system an accelerometer and a microphone, I would like to design 2 different networks which has to coexist on the same microcontroller. So these are the 4 requirements, and the solution that we designed is embedded on the tools. So let me quickly show you how the tools look like.
Danilo, what were the 4 requirements?
The fourth requirement is the capability to enable the sensor unit as a sensor hub, which means to instantiate, I wasn't clear, thanks, to the capability to instantiate multiple neural networks.
Gotcha.
For example, one designed for each specific sensor which is attached to the microcontroller. That is the tool, an example of the tool. This user interface you see is the user interface of STM32CubeMX. Essentially, CubeMX, you can download for free, is a tool that allows you to configure a chip. You select a microcontroller, you configure the clock, the pins, the caches, and you generate at the end through a code generator a template which you can customize as you wish. What we added in the center is that you see through a UI is Xcube AI, the current version that allows you to instantiate multiple neural networks. You see here, I have the baseline, the reduced quantized, the tiny one quantized, tiny 2, tiny 3, and so on and so forth. So I can instantiate them and I can generate multiple networks automatically through the generation code facility. Now, if I go in main, obviously I prepared all the project, otherwise it will be too long. But in the main, you see a quick comparison, hopefully, of the different neural networks. So you see the baseline. The baseline is 1.38 megabytes because I applied the compression of the fully connected layers. However, the complexity is more than 20 million multiplication and additions. And then through the reduction of the network, I was able to reduce dramatically, even by 2 orders of magnitude, the complexity, as well as the memory. Further help I had through the quantization of the network. So let me, for example, get the tiny 2. If I analyze the tiny 2, the code, the network will be imported by the tool in his own format and will be completely profiled in terms of operations, in terms of memory. So what we get is a detailed profile of the network in terms of multiplication and additions, less than 400,000, in terms of footprint for the weights, which is 30 kilobytes, and in terms of RAM requirement, which is 24 kilobytes, but because 12 are due to the activation of the neural network, 12 for the inputs, 12K, and 12 bytes for the output of the network. Now I know the impact of the network on my microcontroller. Furthermore, what I would like to do is to, after validation, validate the network, which means I would like to make sure, and that was a customer requirement, that the code generator generate code which is accurate as the original network. Because, you know, the customer or the developer may spend a lot of time in training precisely the network. So wouldn't like to see any loss in accuracy due to a code generation process which is out of his control. So with validation, we do exactly that step, which means that we generate the code on x86, compiling with GCC, stimulating with random samples, and then measuring the output versus the original model, which essentially says that I run the original Keras model against the converted C model, and then measuring the relative L2 error, which in this case is 0, which means that the conversion was lossless. Whatever we applied, whatever optimization, allocation in memory, whatever trick we applied, we are just making sure to the customers, to any developer, that the code has no penalty in terms of accuracy. The C model will be as accurate as the original model. The third step is to run the model on the microcontroller itself. Now, you see that I have many of those models. I instantiated all the examples I was quickly describing, and I put on this board that I'm showing in front of the webcam. This is a Nucleo board, H7, 480 megahertz with 2 megabyte flash embedded, 1 megabyte RAM integrated. So I already flashed the code inside to save time. What I'm going to do is to execute the network on the target itself. So I'm going back to Tiny2 and running the validation. Now the validation, since I already flashed the code, the validation will generate inputs, will transfer those inputs through the USB cable to the board, to the Nucleo board, run the inference, which is instrumented because at the end we want to know what is the execution time, and then reading back on the UI the results. So this is what I'm going to run here. And in that way, it started the execution. Maybe is a little bit small, but it says there is no connected board. Let me recheck.
Danilo, while you're doing that, just a quick heads up that we got 10 more minutes.
Yeah. Yes. Sometimes it happens when it doesn't recognize, but maybe I didn't set properly the board. Yeah, it is running. I just need to reset the board. So it is running 10 samples, and at the end we'll get the results with a precise profiling. Precise in profiling, which is reported here, 6 milliseconds. So all the process is automated. The second example I want to show, that's part of the methodology is called validation on target. There is another built-in application that is automatically handled by the tool, is the system benchmarking. What I'm going to show you here is, without the involvement of the UI, is that I generated such application with the tool, and then I'm going to connect with the Nucleo H7, which I flashed. And now what it happens is that it's executing one after the other all the networks which I listed before. So in that case, this is the Tiny2 6 millisecond, the Tiny2 integer 8 2 millisecond, and one after the others, also the Tiny3, the Tiny3 quantized, the reduced, and so on, which means this is an example of the multiple instantiation of the network, of the networks on the same microcontroller, which actually act as a sensor hub. There is no RTOS, so in time sharing they are using the same platform. Now, let me go to a quick conclusion, because at the end I would like to demonstrate why all these efforts was, in which direction was leading me. Consider the Tiny2. The Tiny2, if you look, is just 7 kilobyte of flash. And if I analyze, this is only, just a second. This is only 11 kbyte of RAM. So the Tiny2 quantized at integer 8 is 11 kilobyte of RAM, 7 kilobyte of flash. Now, such a guy is an overkill, okay? Too powerful. Now, the lower extreme of the microcontroller family is this guy. It's a Nucleo board with F303, which is an ARM Cortex M4, 16 kilobyte of RAM, 64 kilobyte of flash, 72 megahertz. I already flashed it. Another thing, you see, there are no sensor attached, okay? That's the pure motherboard with the MCU. So I flashed the Tiny2 int 8. I'm going to plug it on my PC. By the way, these Nucleo boards are very cheap. Then I'm going to open a Conda environment in which, and give me a second because I need to open my I need to open the lid of my PC to open the webcam. So let me just stop the video. Okay, and share the screen. Okay. Do you see still my screen?
Yeah, we still see the Anaconda prompt.
The Anaconda prompt. Okay, fantastic. Now let me run. Basically, this Python script is attached to the Nucleo board and is going to use my webcam. What happened here? It happens when the webcam is busy, but I'm not using the webcam. Why this? It seems there is a conflict on the webcam right now. I don't know why, but I have a conflict on the webcam.
I think Zoom uses your webcam by default, even if you're sharing your screen.
Let me, yeah. So what I wanted to demonstrate is that attaching the webcam through the Python script to the firmware flashed on the Nucleo board, I could get a picture from the webcam, classifying using such a picture, and then running the inference on the board and let the classification results to happen on a UI. I don't know why I have such a conflict, but basically that was the reason. It happens. I don't know how to set this particular environment. I'm sorry. Okay, never mind. Maybe I will produce a video for you to have a look later. But yeah, maybe let's do like that. Share the screen once again. And okay. So what I had on the microcontroller was exactly, I'm resetting the board, the network that was ready for simulations, for execution, sorry. Which means that now if I go back to the UI, maybe I can do it through the UI, yes. And I run the validation on target.
Hi folks, while Danilo is doing that, I just launched the poll, so would appreciate it if everybody fills it out.
So what I'm doing, basically, I'm running the inference on the F303, running the Tiny2 quantized 8-bit on these very small devices. In that case, the execution time is 300 milliseconds. Now, the point is that since this was not a critical application, time critical application, it could fit. So I think I'm running out of time, and apologize for the demo not to run properly at the end. However, really, the point is that with the tiny machine learning and by cleverly redesign the network in order to exploit the limited resources on the microcontroller, an application can be also shaped using very cheap hardware, which is not featuring any sensor, exploiting other sensor which may be attached to your computer, like the webcam and so on. I think I stop here for the time being. I don't know if there are other questions.
Thank you so much, Danilo. That was really cool. I especially really liked seeing how well your tool profiles all the models and whatnot. From my perspective, I know that can be a huge pain to do manually. So that's an impressive feature set.
Yeah, this is awesome.
Yeah. I think we can throw it to questions from the class if people have any.
Yeah, the primary takeaways from this class, folks, I just thought I'd summarize, it'd be like, it's important for you to recognize that there are different software frameworks, and also start appreciating the complexity that, some of the points that Danilo was hitting on, which was about developer experience. So these are things that you and I don't think about when we're just kind of talking about neural networks and models, but in practicality, as a systems person, these are the things that you're dealing with. So we'll be spending much more time on this as well when we read the TensorFlow-like micropaper. So I think that's one thing to focus on, is the heterogeneity that you have in the software, the developer experience, and then the hardware heterogeneity that you have to deal with. And some of the things that Danilo touched on, which is about like, how do I support multiple models and so forth, are things that we're not really doing in class, but it's something that we can discuss about multi-tenancy and multi-threading aspects. And the last point is about this benchmarking profiling that Kobe mentioned. In fact, we're going to have Nat Jeffries from Pete's team come and talk about some of the profiling APIs, and Kobe's going to talk about some of the TinyML perf related work as well, more towards once we wrap up the embedded systems. So those are some of the big reasons why we wanted to touch on these topics.